Lesson 3-1, graphing quadratic functions. This is on page 131 in your book. Right. So we are looking at parabolas. You guys are going to see parabolas all over the place here. And you guys know some formulas for parabolas. Actually, the first three examples in your book, they lay out these three main forms to write parabolas. So there's standard form, like y equals ax squared plus bx plus c. Now where does a, b, and c be numbers, like y equals 3x squared plus 2x plus 4, something like that. You can have this vertex form, like y equals a times then in parentheses x minus h quantity squared, and then plus k, where you can very quickly identify the vertex at h comma k as a coordinate, right? And then capital A, this is the stretch factor, the vertical stretch factor. Okay? You can also have a factored form, right? So x minus p, x minus q, where p and q could represent the x-intercepts. You can very quickly identify the x-intercepts. Right. And then again, a vertical stretch factor out in front. So every one of these forms has some kind of advantage to it. Right? Like the first form, if you get the set equal to 0, you can apply the quadratic formula to identify the zeros. Right? The factored form, you get the zeros pretty much right away, just this P0 and Q0. And this vertex form, you can very quickly identify the vertex. Right? So here, so we got, so that's what they spell up. Okay, there you go. There's standard form. I just showed you guys. Right, there's what a parabola looks like. Right, there's the vertex. It's either the lowest point if it's pointed upwards, or the highest point, the maximum if it's pointed downwards, or either the max or the min. Right? Could be the vertex. We got here graph a quadratic function by using a table. Guys, remember, you can create any graph by setting up a table and just plotting a bunch of points. Like if you have no idea what a graph looks like, this one right here, x squared plus 2x minus 3. So f of x equals that, or y equals, you might use that somewhat interchangeably. Let's say you had no idea what that looked like or how to make it. You could just set up an xy table. So they did an example here. They plugged in values for x. They went -3, -2, -1, 0, 1. Right? If that was kind of off base, then you just keep making up values of x and plugging in a checker. But so if you plug these values in for x, for example, 0, right? I'll try 0, right? If you plug in 0 there and there, these bits would zero out. You get -3, and well, okay, they didn't fill it out here, but 0, -3, and they did plot the parabola there. So 0, -3. I do see that point right there. Okay. What else have we got? What if I plug in -1? -1 squared is +1. 2 times -1 is -2. 1 minus 2 is -1. Minus 3 is -4. There should be a point -1, -4. There it is, right there. There. You can just keep plotting points until eventually the graph naturally emerges. Right? You can always do that. Right? Maybe that's a good quiz tip also, right? Like I have guys draw graphs on quizzes. If you had no idea what the graph looked like, you could always do this table method. So you can do that, right? Right. But you can also let's see, apply some tricks right here. Well, I'll take out some tricks for this particular one. Right? So let's say they say f of x, so let's call it y, right? Same idea, right? X squared plus 2x minus 3. Right? Like, this one should be factorable, right? And there are different ways to factor. Right? So I could do something like this, right? I throw x, this is like reverse FOIL, FOIL, backwards of that, where two numbers that add to +2 and multiply to -3. I think that would be -1 and +2, wouldn't it? Did I? Or sorry, 3, +3. Okay. Let me double check. Okay. So let me try with FOIL. FOIL. That's first, outside, inside, last. So x times x, x squared. 3x minus x, 2x. -1 times +3, -3. Yeah, okay, so it checks out. And then, now that this is in factored form, and maybe that's easier to work with, because in factored form, I might know something like, I can very quickly try to, maybe make an XY table again, right? X, Y, and I make some values. Right? But it very quickly can spot what are the x-intercepts. Because watch this. If I plug in 1 for x here, 1 minus 1, this would be 0. And 0 times anything, well, the whole thing would just zero out. So I know if I plug in 1 for x, I will get 0 for y. Hence, that would be an x-intercept. So there has to be an x-intercept of 1, 0. Okay. And the same is true for -3. Right? If I plug in -3 there, this bit zeroes out, the whole thing zeroes out. So -3, 0. So right there. Okay. Now, if those are my intercepts, I know the vertex has to be right in the middle, and right in the middle is like -1, so I can plug in -1. Okay. See, -1 minus 1 is -2, -1 plus 3 is +2, -2 times 2. Oh, hey, we did that earlier. We did that just a couple minutes back. Okay, I've got -4, 2, 3. So this is the coordinate, -1, comma -4. Take down here. Okay. And since I know that is the vertex, then I could really just get the entire graph from that. Right, so it's got to look like oh, I could also get the y-intercept. Why not? If you plug in 0 for x, 0, 0. So this it becomes 1. This becomes, sorry, this becomes -1. This becomes 3. So if I plug in 0 for x, -1 times 3 is -3. That's this point right here. All right, so little step, right? Yeah, so it lines up. It's all good. You can always do that method. Yeah, so they leave. You know what? Before I leave the standard form, one of I should really say about standard form is that if you have y equals ax squared plus bx plus c, right? And then you go ahead and set that equal to 0. So not y equals anymore to make a general graph, but I'm specifically looking for the x-intercepts. And so x-intercepts, also called zeros, aka also known as zeros. Right. Then, right, so I'll say if this is true, right, you could say y equals, but then instead of equals 0, then this has sort of been pre-solved for you guys already with quadratic quadratic formula. I should get it right here. Okay. So -b plus or minus the square root of b squared minus 4ac, all collectively divided by 2a. Okay. Now there's a lot juggling here, so make sure you are correctly grouping values in parentheses. Like so, all this is underneath the radical, for example. All this is in the numerator. All this is in the denominator. So make sure you can correctly communicate that to your calculator. All right, let's try it for this because all right, this example they did give us the standard form. So I'm going to try the standard form of this one. All right, so x squared plus 2x minus 3. X squared plus 2x, yeah, minus 3. Okay. Now I said y equals, but I'll say equal to 0. You might try this out. I bet I get the same zeros that I got before, okay, because I already know what the answer should be from a few minutes ago. Let's see. Okay. So x, like the zeros, would be -b, so that's -2, plus or minus the square root of b squared, so that's 2 squared, minus 4. Isn't there an applied 1 coefficient right here? So that's like your a value. And then c is -3. Okay, so make sure you're juggling all the negatives and so on. All right. All collectively divided by 2a. So that's 2 times 1. Let's see, that's -2 plus or minus, let's see, 2 squared is 4. All right, 4 times 3 is 12, and the negatives do cancel here. So I should do like, okay. So what is 4 plus 12? That's 16. The square root of 16 is 4. Okay, you got a plus or minus there. All collectively divided by 2. Now, -2 plus 4 is 2 divided by 2 is +1. Right? Or if I subtract off -2 minus 4 is -6 divided by 2 is -3. Okay? So that would correspond to the points 1 comma 0 and -3 comma 0. Okay? Go back and check my graph and see if those are in fact the zeros that we already got on the graph. So +1 0, -3 0. See, is that exactly what it looks like? Oh yeah, that's those right there. Oh yeah, oh yeah. There's -3 comma 0. There's 1 comma 0. Yeah, that's it. That's totally it. Right there. Yeah. All right. So vertex form. They'll give you. Okay. Well, how did I write it? I wrote vertex form at this vertex form right here. That's y equals some vertical stretch factor x minus h quantity squared plus k. Okay. Therefore, the vertex would be at the coordinate h comma k. Right. Keep in mind, horizontally, you're subtracting off the x coordinate, and then vertically, you're adding the y coordinate for the vertex. Okay. Okay. So in this case, let's look at this here. What are the? I think there's graph under here, but let's just copy this down and see if we get the same thing they do. y equals 1/3. We got x plus 1 quantity squared and then plus 2. Right? So I should be able to graph this just from like these rules, like these vertex and structurals. Let's see, plus 1 would then be to the left 1, and plus 2 would be up 2. So maybe I should go over here make this x, y. Okay, so plus 1 this way, plus 2 this way. Pretty sure the vertex should be right here at -1, comma 2. Right? But you can try it out, right? If you plug in -1 here, this zeroes out, plus 2, yeah. Right, so if you plug in -1 for x, you do get 2 for y. So that's definitely the point. That should be the vertex. Okay. Now, if I drew like a regular parabola, but ignoring this 1/3 for a moment, I know it goes like over 1 up 1 would be a point, over 2 up 4 from the vertex, right? Right, would be a point, right? I could draw a regular parabola from there. Okay? What the 1/3 does is it's going to squash everything vertically 1/3. So I should get a point right here. This would be at what? 1, 2, 3, 4, 5, 6, 7/3. So I think 0, comma 7/3 should be the y-intercept on the graph. Right? If I go to the left one, so something like that there. It's going to make a wide, shallow looking parabola. It's going to look something roughly like this. Right? Real wide and shallow looking parabola. Okay? Let me double check, make sure this does work. If I plug in 7/3 for x, or sorry, if I plug in 0 for x, I should get 7/3 for y. See, 0 here, that's 1. 1 squared is 1, times the third is a third. 1/3 plus 2. Okay, times third. Yeah, that would be 7. Okay, 7/3. That's exactly what it is. Did they give us? Oh, no, they didn't. Oops, I thought they would have. Right, but that's what it will look like anyway. So you can do that version. Okay, graph the function. Okay, that was vertex form. Here's factored form. Okay, so factored form. Right, it's factored form right here. I was showing you guys earlier. Y equals. Right, maybe you might have some vertical stretch factor. Got x minus p, x minus q, where p and q would represent the zeros. So you can immediately get the zeros for the x-intercepts. Okay? So the example they gave us is we've got a -2, we got x plus 2, and then x minus 1. Okay? Well, here, let's get a set of axes going right here. Yeah, x-axis, y-axis. Something like this here. Right, so I know if I plug in 1 for x, this zeroes out, so the whole thing zeroes out. So that's the vertex right there. Or sorry, not a vertex, a x-intercept. Here's an x-intercept right there. Okay. I know if I plug in -2 for x, this bit would zero out. 0 times the whole thing would also be 0. So that's an x-intercept right there. Okay. Furthermore, I know the vertex is going to be exactly halfway between those two intercepts. Okay, so this one's a little weird. So it looks like -1/2. All right, let me consult my calculator for this one. What if I plug in -1/2 to this expression? It should tell me exactly where the y-intercept is. Okay, I can guarantee, I know enough already that do you guys see this -2 vertical stretch intercept? That means isn't the graph going to be upside down, like an upside down parabola, which means the vertex has to be in positive territory. Right, so let's do it. And so if I plug in -1/2 here, I get, say, -2 times, then parentheses, -1/2 plus 2, and then -1/2 minus 1. Right, that should get some positive number, which should represent the maximum on the graph. Yeah, it's 4.5. 4.5. Let's stretch this a little bit. Let's go 1, 2, 3, 4, 5. Put 5 up here. Right. 2, 3. Okay, so we'll squash graph. Right. This right here is the vertex. And the vertex is at the point -1/2, comma 4.5. Okay? And the rest of the graph would follow. So it would look. Actually, let's see where the y-intercept is. It looks like it's going to be fairly close to 4, right? So if I plug in 0 for x, you got a little xy table, right? X, y. Okay. And then if I plug in 1 for x, I get 0 for y. If I plug in -2 for x, I get 0 for y. If I plug in -1/2, I get 4.5. We got those points on the board already. What if I plug in 0 for x? Figure out what's the y-intercept. So 0 here, 0 here. I get 2 times, so negative 2 times positive 2 would be negative 4, and then times negative 1 would be positive 4. Yeah, that's exactly where it looks like it would be on the graph anyway. I'm saying pretty close to 4, and it is 4. Goes through 0, comma 4. Yeah, there you go. Yeah, that's that graph right there. Um, Speaking of the vertex of a parabola, okay, you can also get that from quadratic formula. So, yeah, the quadratic formula, okay, you can use it the way I told you guys a few minutes ago, but there's some features that you can use to figure out other parts of this parabola. Like here, right here, you see it's negative b over 2a, negative b over 2a. Now, this is working from standard form. Okay? That would have to be the dead center of the parabola. So this would tell you the x location of the vertex. Okay. And then from there out, this plus or minus square root whole thing, blah, 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 right? You're like branching out left and right from that central vertex. Okay, so this tells you the x coordinate of the vertex. So okay. Here, I'll try it for this one. What if I expand this whole thing out and then I look at the quadratic formula? It should tell me the x vertex is right here, okay, at negative 1/2. Let's see if that's true. So if I expand this out, I'll FOIL this. Let's see FOIL. Okay, so here, I'll get the negative 2 later. Got first. Outside inside x. Negative x plus 2x gives you plus x. Right. And then 2 times negative 1 is negative 2. Right now, if I just distribute that negative 2 after the fact, okay, I'll get y equals negative 2x squared minus 2x. And then negative 2 negative is plus 4 right there, isn't it? Okay, something like that. There you go. Okay. Now, what I'm saying is, if I were to like set this equal to 0 to get the x-intercepts, which would be here and here, okay, there is a part of the quadratic formula, it's that negative b over 2a bit, that would tell me exactly where the vertex would be. And it should be at negative 1/2, because that's what I figured out before. Okay. Actually, I'll just jump straight to that. Okay, so x vertex would be at negative b over 2a. Well, your b is negative 2, and your a is also negative 2. So that's negative, negative 2, it's negative b, right? Over 2a, just like this. Yeah, oh, hey, look at that. The negative 2's conveniently cancel. So isn't that negative 1 over 2? So, oh, yeah, yeah, that's what we got. That's exactly what I said it was going to be. Right? It's just a different way of looking at it. It's a different way to get there. Right? So if you know how to read the music of these equations. Okay? Well, I'm pointing out different aspects of the quadratic formula. Okay. You guys also remember this right here underneath the square root is called the discriminant, this e squared minus 4ac. And it tells you how many times this equation will cross the x-axis at all. Okay? Like here, I'm getting 2 zeros. Okay? And that can be because, remember, you're only allowed to take the square root of positive values. So if e squared minus 4ac is positive, then it'll always cross twice. If it comes out to exactly 0, you get plus minus 0, which you only get one case, which means the vertex would be somewhere exactly on the x-axis. And if this whole thing comes out to negative, e squared minus 4ac is negative, well, a square root of a negative would be imaginary. It wouldn't even give you a real value, but which means the parabola would not even cross the x-axis. Maybe it's like down here, or if an upside or upright parabola would be like up here, but it will never cross the x-axis. All right, so I bet you guys remember that from before. That's just a little bit of review. Okay. All right, what else here? Write a quadratic function from the graph. Ooh, hey, let's look at this graph. I want to cover this up because I don't want to cheat and get the answer yet. I want to see if we can figure this out from scratch or something. Right, so what are some points on this graph? So I'll say example 4. Right, we're going to come up with an equation. Right, so here, I'll make like an XY table, except this one I'm picking the coordinate straight off the graph. Okay, and then I'll figure out how to make some kind of formula from that after that. So it gives us the vertex right here. If you plug in negative 2 for x, you do get 5 for y. Great, so we've got a vertex. Okay. What other point do I see? Ooh, I see this point right here at negative 1 comma 2. So negative 1 comma 2. And also 1, 2, 3, 1, 2. So negative 3 comma 2. Okay. Now if you keep plugging in more points, okay, but that's really all you need. Okay. Now there's a few ways you can figure this out. Some of you guys might already see this, right, that from this vertex, okay, on a regular parabola, just like y equals x squared, you can go over 1, up 1, or right, to get another point. This is like over 1, down 3. So I already know there's sort of like a vertical stretch factor of 3. It's going to be like a negative 3x squared. So of course negative because it's upside down. Okay? So I'm already imagining that. Okay. Now we have different forms we can put this in. We do standard form, vertex form, factored form. Now the factored form is a little tricky because just eyeballing the graph, I can't immediately discern exactly what these x-intercepts are. So I'm not going to worry with that. Let's try the vertex form. So I'll consult vertex form. Now vertex form goes y equals, okay, so some stretch factor, and then x minus h quantity squared plus k, something like that. And what's really nice about this is I know what h and k are for the vertex. That would be this point right here. Okay? Right, so this k would be 5, and this -2 would be this h right there. Right? And then I can take one of these other coordinates and plug them in for x and y. Right? So yeah, that's like x and that's like y, right? Okay. Let's say, how about this one, for example? Okay, it could be either one. Right, so if this becomes my y value that corresponds to this being an x value, and that is a specific point. But what that would allow you to do is to solve for this a. Remember, I already know what a is going to be just by eyeballing the graph. I already know it's going to come out to -3. So if it comes out to anything else, then I messed up somewhere. But this a has to be -3 because it's vertical stretch of 3 and it's upside down. Okay, so let's see. Plug all this in, see what happens. Right, so here, well, first I'll start off real generic. I'll say some generic y equals a x. All right. And then for h, now h is always going to be this -2 because that corresponds to the vertex. So that's just kind of like baked into this equation, right? Something like that. And then same thing for this k. Right? Right, so the final form is definitely going to have something to do with these two numbers being here. Right? And this x and y could be anything, but a cannot be anything. It's got to be something specific, and that's where we're going to bring in this point right here. So -3, comma 2. You could have also gone with -1, 2. So I'll do this one. So if y is equal to 2, that's going to correspond to x being -3. Okay, and now we can solve everything else. Minus a -2 is the same as plus 2. This will be squared and plus 5. Okay, so now we can solve for a, and then we'll have the whole thing. And so 2 equals a that we're solving for. All right, this is -1 being squared plus 5. Right? Well, -1 squared is 1, so that just kind of goes away, doesn't it? Right, subtract over 5, -3 equals. Oh, yeah, there we go. There we go. Right. Remember I said a had to be -3, and if it was anything else, then I messed up. Oh, okay, well, we did everything right. So that's it. All right, so last thing is, let's piece this whole thing together. Now, it's going to basically be this form with this vertex popped in, right? And then, but now I know what A is, this vertical stretch factor. So the answer is y equals, I got -3, I got any x value, so like as a variable. Okay. Now minus a negative, I could just go ahead and say +2, that's okay. Okay. Squared plus 5. Okay. So this is the equation of that parabola in vertex form. Vertex form. Okay. Hey, what if I wanted standard form? Can I do that too? Yeah, you just play around with this. Like I started with vertex form because that was, I think, the easiest way to solve for it. But what if I want to put this in standard form? Let's try it. So y equals -3. I'm going to FOIL out this bit. X plus 2 quantity squared is not like this. And then tie on the plus 5 after the fact. So keep this -3. Let's do FOIL. FOIL this thing. So that's x squared plus 2x is 4x. And 2 times 2 is 4. Okay, and then I'll worry about the plus 5 later. I have to distribute the -3 in here. So it looks like y equals -3x squared minus 12x minus 12, and I have a plus 5. Okay. And last thing is bring these two together. So y equals -3x squared minus 12x. This would be -7, wouldn't it? Okay. So that's the same equation in standard form. Okay. Same equation. Okay. Okay. So there could be two answers that like this equation and this equation are the exact same thing. This one's in vertex form up here. This one's in standard form down here. Right? And just to prove to you guys that that's true, here I'll pick one of these. Remember, this table of values has to be true. I'll pick one of these and plug it in and show you guys that this does work out. Okay, so all right, so let's say, how about this vertex at -2, comma 5? So if I plug in -2 for x, I should get 5 for y. Okay? So let's do -3 times, and then -2 being squared. minus 12 times negative 2, and then subtract off 7. Right, I've got to get 5 out of this. Oh, yeah, it totally is. Totally is 5. Yeah, yeah. Right. So just double check, make sure the standard form worked. It sure did. Moving on. Now, what's next here? Write a quadratic function from a table. But what if they just give you a table of values? You got to figure out from there. Um, so what do you do? Well, I guess there might be different ways because I don't really know what part of the problem this is, but if I plot these points on a graph, I think I could figure out pretty quickly what it kind of looks like. Right, so it looks like the x, we're looking at sort of the negative territory close to 0, and the y is well, positive, negative, right? So they're giving us, I think it's going to fit right here in this space, x, y, okay, straight. All right, so x goes back to -4, it's like something like that. Y goes from -1 to +3. Okay? So they give us -4 comma 3. So that's this point here. They give us -3, 0, -2, -1, -1, 0, 0, 3. Oh, yeah, yeah, yeah. Look at that. Look at that. Right, right. Now I know what's going on. Right, right, there you go. Right. And there's different ways you can put this together, but now we're back to a graph, which is kind of what we did for this one. But you can definitely see this one's even simpler because look at this. There's definitely the vertex at -2 comma -1's vertex. Okay? And I see from there if I go over 1 up 1, I also land on the parabola. And over 2 up 4 from the vertex is another point. Okay, so this is just a regular parabola. There's no like a term in front of the x squared term. Um, and uh, here, give you guys some different forms. Vertex form, vertex form would go y equals or f of x equals, pick a favorite. Uh, all right, so x minus h. Now that looks like x plus 2, right? Because it would be minus -2, quantity squared, and then -1. So you could do that. Okay. You could go factored form. Factored form. So y equals, okay. And then play off these two x-intercepts. So it'd be like, what was this, -3? So x minus -3 is that like x plus 3? And then this one's x minus -1, so that's x plus 1. So you could do that. This and this, again, they're the exact same equation. They both refer to this graph, right? And what would this look like in standard form? Form. There you go. Well, I could start with either one of these and work it out. Here, let's FOIL this one. How about that? So y equals FOIL. X times x, that's x squared. And then outside, inside, x plus 3x gives me 4x. And then 3 times 1 is 3. Okay, so all three of these refer to this graph. They also say the total same story. Okay, and just to prove you guys that's true, all right, let's try this this y-intercept right here. Should this be the point 0, 3? If I plug in 0 for x, I should get 3 for y. Is that true here? See if I plug in 0 for x. This 0, this 0. Yeah, I get 3 for y. Yep, that's exactly it. That's exactly it. So it all works. It all works. Okay. All right, then they bring in a story example. Now there are definitely some good examples of stories that involve quadratics. I know for physics, just to skip ahead a little bit, physics, like anything in a gravitational field, could follow like its height as a function of time follows a quadratic follows parabola type equations, right? And they do sort of give an example here, like blasting a cannon, fall off the edge of a castle or something, or something like that. So but there are a few examples here where they're using sort of like a business economics example. Like, if we raise the price of something, we'll get fewer people buying it, but the price would be more. So, maybe would we get more revenue or less revenue, and vice versa? What if we put something on sale? Uh, the price would go down, but more people would buy it. So it's sort of like a trade-off, right? Sort of like a trade-off. You can sort of model this with, well, actually, you can model these examples also with parabolas. Okay. I do think they work this a little bit funny. It takes a little bit deep thinking for the first time you do one of these specific examples, but there's a bunch that follow this exact model in this book. So let's take a look here. A ski resort has extended hours on one holiday weekend per year. Last year, the resort sold 680 ski passes at $120 per we can pass. So if you like, how much money were we talking about? 680 ski passes times $120 per pass. That's 81,000 and some dollars. Okay, so 81,000 some dollars in revenue. This year, the resort is considering a price increase. Okay, so they would be making more money per pass, but they would be selling fewer passes because people looking at the higher price. Nah, right, so we get fewer people buying. They estimate that for every $5 increase, they will sell 20 fewer holiday weekend passes. Right? Right. Right. So really anything you could be selling. Here we're doing ski resort, but you could do this like at a grocery store. What if we like raise the price of a can of beans by 5 cents? Right. So okay. So you overlay a lot of different stories on this. How much should they charge in order to, it says maximize profit. Now, if you're taking that economics class, you guys know really they're talking about revenue here. I might just refer to this as revenue. Profit is revenue minus cost. But here, maybe the costs are already like negligible or they're already like fixed or something. Right. So they're really talking about revenue here. And they tell you how to think about this. They said, let's call the variable x. Okay, now here's for me what was the tricky part to wrap my mind around. But once you get past this, you can just use this model a lot of these. Okay? They're going to use x, the variable x, to represent the number of these, in this case, $5 price increases. Okay, so what if we increase by $5, $10, $15? So it's these $5 increments. Okay, and then x is going to be the number of increments they increase it by. Okay, and they're going to use that to model this equation. Again, I'll call this R for revenue because P they're trying to use for profit, but later on in this book they use P for price. So, I'm just talking about revenue. So revenue, say, is a function of X, where remember X, here, label it so it's really clear what I'm talking about. So revenue as a function of X, in this case, represents the number of $5 increment. Correct. It's increment. Let me look that up real fast. It's an I or an E there. Did a quick word check. It is an E. Increment increases. All right. Is equal to. All right. Well, the baseline price was $120 per ticket. So we're starting with that. Right. Plus $5 price increase. Right, times the number of those increases, wouldn't that give you the new price? For example, here, just to check, make sure you guys follow. If you had one of these increment increases, that means you're increasing the price by only $5, which would bring the price to $125. Yeah. If you had two of these, so you plug in 2 for X, this would be 5 times 2 is 10. Now we're up to $130. Yeah, this is checking out. So this would be the new price. But the catch is that the quantity that you sell is going to be fewer. So we started off selling 680 tickets at this $120 price. Okay? But every time we increase the price by $5, we're going to lose 20 sales. So $20 times that number of increment increase. Okay? Really, what this comes from this. Revenue equals, I should have written this to start with. Okay? Price times quantity. Right? Okay, so for example, the original was $120 a piece. That was the price, the original price, okay, without any increases. Okay? At times 680 of those tickets. So their original revenue was $81,000 and some, right? Something like that. As the original revenue. Okay? So you guys see this trade-off. You see this trade-off, right? The more you pump up the price, right, the more revenue you get from because this number's getting bigger. But the fewer and fewer tickets are selling. So, right, so there's this trade-off. You can imagine that if you graph this out, this would look like an upside-down parabola, right? So, like, what's the maximum? Well, there's a few ways that you can find this. Oh, hey, look, the book is actually recommending using that negative b over 2a trick from the quadratic equation that I was telling you guys about a few minutes ago. Okay? So, if we expand this out, like FOIL this out, and put this in standard form, we could just go x equals negative b over 2a. That would tell us exactly x, the number of incremental increases to include. Okay? So if x comes out to 1, we would increase the price by $5. Okay? If x comes out to 0, we'll just leave the price at $120 like it originally was. So, okay, so let's FOIL. FOIL. Okay? Ooh, definitely a calculator in this. Well, this one I did already. So the revenue as a function of price increases equals 81,600. This would be dollars. Okay, dollars. Okay? Let's see, negative 20 times 120, okay, plus, do O and I together because those are both x terms. Uh, well, here, I'll break it down just so there's no confusion here. So minus 2400x, and then inside 5 times 680, okay, plus 3400x, and then finally 5 times negative 20, that's negative 100, and that would be x squared. Okay? Right. Or I can rearrange this, make this, put the x squared term in front and hold it right. And so the revenue as a function of x, the price increases, equals, I got negative 100 x squared, 2400, 3400. Is that 50? Oh, no, sorry, that's positive negative. So 3400 minus 2400 is okay, 1000. So plus 1000 x, and then plus 81,600. Okay, that is the equation of that parabola. Okay. Okay, so I could say x vertex would be at negative b over 2a, which would be at negative 1000, because that's like your b term here, right here. This is like your a, your b, and your c, right? Over 2 times negative 100. Now the two negatives will cancel out, which tells us that, yeah, this would be a positive value. So we will be having to increase the price to maximize revenue. These zeros, that's 10 over 2. I think that's 5, right? X vertex would be at 5. So 5 of these incremental increases, $5 increases, $5 increases. So 5 increases times $5 per increase would bring us to a $25 increase. Okay, $25 increase. Okay. So the new price then on top of the original. So I'll say price new, like the new price equals the old price with price old plus the change in price. So like delta price would be the change in price, right? Okay, which would be $120 plus the new $25. Okay, so the new price we're going to target is $145. Okay, so we're going to increase these tickets up to $145 a piece. Okay. Yes, fewer people will be buying the tickets, although the tickets are more expensive, and this would maximize the revenue. Okay. Like if we sold for anything like $142, we're not going to make quite as much money. $148, also not going to make quite as much money. Is that what the book had? Did well, okay, actually, it looks like they came up with a 5 somewhere. Okay, so that's probably what they got too. Okay. Yeah, this would like kind of fall in what it's a lot of blanks there, but probably it. And I wonder what that would look like on a graph. Let's check that out. Okay, well, it would be positive number of tickets territory. So if I go this way, right? So maybe revenue, and then remember X is the number of price increases, like $5 price increase. Well, should I do that? Yeah, that is what the equation says. Kind of weird. Yeah. Okay. Okay. Okay, something like another graph I could make, which would be different, would be what if I put price over here? Right. It would still make an upside down parabola. Right? You could still figure out the optimal price to maximize your revenue. Right. But if I want to model the equation that we made, we put all this work into and what we're getting in context of, this would be in terms of price increases. Right. Right. So five increases, would maximize revenue. If you had no increases at all, you're sitting at $81,600, I think it was. Okay. But with 5 increases, what does that bring you to? How many tickets would you even sell? Well, what's 680 minus 20 times 5 would be 580. 580 times, and then $145. It'd be 84,100. Oh, so we didn't even make that much more money. 84,100. Okay. Yeah, so this is, yeah, okay. Now I'm seeing this. So 5 increases. This is like a real shallow parabola. It's going to look basically like this. Try and draw that correctly, right? Somewhere there. Okay. Or if we put this in terms of price, let me make a completely different graph. Okay. If we put price on this axis and revenue on this axis. Okay. So it's not going to be the scale, but just get the idea. $120, 145. So $120 we make something. At $145 we make something. We got 81,000 here. Got 84,000 here. Okay, yeah, again, it's not the scale, but you could also make a graph in terms of price. It would still be a parabola, upside down parabola, so something like that. Okay, so there's a few different looks at that. All right, let's jump into these text questions. And so I highlighted some of these. I got some pure math examples. I try to check all the boxes here. And then found a few word questions. Look fairly similar to what we just did. All right, so graph each function, state the key features of the graph. Now, key features, this will open to interpretation. I might say, what's the vertex? What's the x and y intercepts? I mean, that should be plenty enough, right? Okay, so number one, f of x equals x squared plus 6x plus 8, something like that. Okay. Now, there's different ways to go about here. This one I'm looking at, you could factor this, right? 2 times 4 is 8, 2 plus 4 is 6. Yeah, you totally could. You could do factored form. Right. There's other ways too. There's other methods, but I just see that method jumps out to me. You can put this in factored form, standard form, factored form. And from factored form, you can very quickly graph this. So x, y, we got, because I see it negative, where x is -2, this whole thing was 0. If you plug in -2, here, we make a table. Let's make an xy table. Okay. If I plug in -2 and also -4 for x, each of those is going to give me 0 for y, wouldn't it? Okay. So -2, -4. Okay. So there's two x-intercepts on the board. Okay. I also can see already just from that the vertex is going to be where x is -3. So I'm kind of curious where is -3 also, right? So if I plug in -3 here, this comes out to -1. This comes out to +1. -1 times +1 would be -1. So that's like down here. Yeah. Right. One more point I'm kind of curious to know is what is the y-intercept? If I plug in 0, 0, oh, well, actually, no, it's 8, right? It's right here, 8, right? Or 2 times 4, however I do it. So, well, okay. That's kind of off the page here. 1, 2, 3, 4, 5, 6, 7. Actually, okay, kind of fit there. Okay. So 0, comma 8, which is way up here on the graph. Right. That would parabola, parabola. Right. And then the ghost. Right, there you go. Right. Okay, so here's the vertex at -3, -1. Here's the x-intercepts at -2, 0, and -4, 0. And then here's the y-intercept up here at 0, comma 8. Right? Yeah, so those could be some key features, right? All right. Next one. Number 2. We got f of x equals negative, and then x plus 1 quantity squared, and then plus 3. All right, now that's in vertex form. So I can very quickly pick out the vertex at -1, comma, +3. So -1, 3. So maybe something like this. X, y. Maybe that should do it. Okay. So here, if I make a table of values, x, y, I know if I plug in -1 for x, this whole thing zeroes out, and then I get +3. So -1, 3. And that, by the way, is the vertex at -1, 3. That's the vertex. Okay. How about what if I plug in 0 for x? Let's see if I can give you the y-intercept. I bet it's going to be right here. Just looking at, no, this is an upside down parabola, right? With no vertical stretch. I bet it's got to be right here. So let's plug in 0 for x. This is 1. 1 squared is 1. That makes it negative. -1 plus 3 is 2. Yeah, it totally is. Totally is. Right there. Okay. I bet if I plug in -2 for x, I get the same y value right here, just by symmetry, right? By symmetry. So plug in -2. This would be -1 squared is 1. Then this makes it negative again. Yeah, same thing. Right there. Right? Now the x-intercepts is a little trickier. It's got to be somewhere between 1 and 2. You can set y equal to 0. Here, we could do that. Right. What if I want y to be 0? Right. I'll have to work this out algebraically. Let's say 0 equals negative x plus 1 quantity squared plus 3. Subtract over 3. The negatives cancel, square root both sides. Now remember, when you square root, going through this algebra method, we do plus or minus. X plus 1. Subtract over 1. So x for the zeros would be -1 plus or minus the square root of 3. Square root of 3 is like 1.73. Yeah, so be 0.73 right there. And -1.73, -2.73. With it. Yeah. That's aligning exactly with that graph. That's exactly what it should look like. Right there you go. Right. So we got vertex, we got y-intercept, we got this symmetrical point over here. We got a couple of x-intercepts, which are a little trickier to work out. It's a -1 plus or minus the square root of 3. Right, okay. Right, those are there too. Okay, number 6. Number 6. F of x equals x minus 2, x minus 4. All right, so this is factor form. Now, from factor form, we can very quickly figure out what are the x-intercepts. Okay? So it's kind of the last thing we did on the previous one, but that was a little tricky to dig down. Had to dig through some algebra, got a funny looking answer. Okay? But this one, we got them right away. Right? That's kind of the first thing that we know. Right? So at +2 and +4, so let's go. So better like list x, y, right? Okay. Should have gone up a little bit more. Sorry. Okay. Let's make an XY table, right? If you had no idea. Okay. Well, I know if I plug in 2 and 4, each for x. 2, the zero's out there. 4, the zero's out here. The zero's out, right? I see the vertex is going to be where x is 3. It's got to be between those two. 3 minus 2 is 1. 3 minus 4 is -1. 1 times -1 is -1. So that's this point right here. Okay, I see what the problem is going to look like. I'm curious, one more point. What if I plug in 0? I get -2 here. I get -4 here. -2 to -4 is +8. That's 2, 4, 6, 8. That's this point right here. 0, 8. Okay. Yeah, there's a bunch of points. Right. So probably those points would be the 4 points of interest, wouldn't it? So the vertex is at 3, -1. The zeros are at 2, 0, and 4, 0. And the y-intercept is at 0, 8. Yeah, so there's some interesting points, right? Key features. Right, number 7, write an equation that models this function. Right. So let me just through a couple here. Now, interestingly, both of their examples, looks like there's no vertical stretch factor. And you can know that because if you look at the vertex and you go like over 1, down 1, or in this case over 1, up 1, you also land exactly on the parabola. So there's no vertical stretch. Okay? So okay, let's get some XY values and figure out what from there, right? So I see if I plug in 1 for x, I get -1 for y. In fact, that is the vertex right there. And then if I plug in 0 for x, I get -2 for y. If I plug in 2 for x, I also get -2 for y. Okay? How about vertex form? Let's go to vertex form. Okay. So I'll do y equals x minus h quantity squared plus k. Okay. Now you could have this a stretch factor, but that's just going to be 1 from this graph for the reason I just said a minute ago. Okay. And so I see the vertex is at 1, -1. That's it. So f of x equals, okay, so a is going to be 1, x minus 1, then that's squared, plus, and then y is -1. Okay. Let's put it all together. F of x equals x minus 1, quantity squared, minus 1. Okay, that should be it right there. Okay. Here, I can check a point. Let's check this 2, -2 should work, right? So if I put in 2 for x, 2 minus 1 is 1, squared is 1. Hold on a minute. No. I did miss one little detail. Guys, this is upside down. Oops. So a is something. A is -1. Oops. Okay, good thing I checked. Okay, so there. Now it's fixed. Right, what we now. Okay, so let's go back and double check. So this should work now. If I plug in 2 for x, 2 minus 1 is 1, squared is 1. Now it's negative. Aha! So we got -1 here, minus 1 is -2. Bing! Okay, we're good. All right, let's do number 10. Okay, number 10 is where they give you a table, and we're supposed to come up with an equation from this table. Remember what I did before in examples is I just started plotting all the points and saying, well, I wonder what the graph looks like. Yeah. So number 10, how extreme does this go? Whoa, okay, y goes to negative 67, and it goes up to 5. That's interesting. And the x goes from negative 6 to 6. This is going to be a big old graph, isn't it? Could potentially be. There's a lot of negative territory. So, actually, where is the vertex? The highest point is where x is 0. Okay, so it is centered on the y-axis, so it's not like moved left or right at all. Okay, so I'll put x here, y here. Okay, we want to like 60 something? Wow, okay. Let's go 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. I probably don't even need this much to figure this out, but okay. Okay. Let's go. Actually, let's not even go that far because that's really extreme. Um, let's go to how about negative 27? I think makes more sense, right? So we'll go uh, so 1, 2, 3, 4, 5, so there. Let's go 5, 10, 15, 20, 25. Right? So this is really squashed vertically because it's like 1, 2, 3, 4, negative 5, negative 10, negative 15, and so on like that. That's really right. Yeah. All right. So then 5 would also be up here. So we got the point 0, 5. It goes right here. This could be the point 0, comma 5. Right? Now from there, if you go over two. Okay, I'm interesting. I want two at a time. Then negative 3, 2, negative 3. That's like right here. And then 2, negative 3 right here. Right. So what is that gap? Okay. So I know my standard parabola is like over 1 down 1 would hit a point. But here if I go over 2 down 8. Hmm. Hmm. Okay. Right. This is gonna continue on this way, right? Right. So there could be a few ways to do this. A few ways to do this. All right. See if I can figure out. Right. I don't really want to do factor form. I could do vertex form. Yeah, vertex form could be there. Right. I'm thinking some other ways I could do too, but let's try vertex form. Vertex form. Right. I think that worked last time. Right. So y equals some stretch factor x minus h quantity squared plus k, something like that. Okay. Um, right. Well, this minus h would just be 0. Okay. So this is just 0 because it's sitting right on the y-axis, the vertices. Okay. And this plus k would be equal to 5 because I also see that vertex there. Okay. So this is like y equals a x squared plus 5. That's, okay, so this is really the form it's going to take. Okay. I just have to figure out what a is. Okay. And I can figure that out by plugging in any of these other points. And I have a point right here at 2 comma negative 3. So let's try this point. Plug this point in right here. So when y is negative 3, x could be 2. X could also be negative 2. Right, okay, yeah, squared. Yeah, of course that would work, right? Okay, now I can solve for a. Once I have a, we'll have the whole thing, and we'll be good. Okay. So subtract over 5, that's negative 8, equals a times, now 2 squared is 4. Divide both sides by 4. Oh, negative 2. That's not too bad, right? Right. So put it all together. I'm getting, here, I'll make it f of x, look fancy, right? Like a function. Uh, my a is negative 2. Then I got my x squared. I got this plus 5. Okay. That should be the answer right there. Should be the answer. Okay. And just to make sure, I'll pick any of these other points. How about 4 comma negative 27? Okay. So if I plug in 4 for x, I should get negative 27 for my y value. Let's see, if that's true, then this is definitely correct. Okay. So 4 squared is 16 times 2. Well, 2. Okay, negative 2 times 4 squared. Right, and then plus 5. Yeah, it is. It sure is. Look at that. Negative 27. Oh, yeah. Oh, yeah. That is good. Good. All right. All right. So that's the pure math examples. Um, you know what? Okay. Let's do this. I had a few of these word puzzles picked out. Um, Oh, three of these are like that business economics one that we did before. Right? Uh, so I'll pick one of these because they're all sort of the same. Okay. Let's do this one with the candles because this one we're kind of putting candles on sale, which is like subtracting from the price. Okay, so that's a little different. Okay. And then we'll flip over and we'll do this cannonball one, maybe this physics one. Ooh, right. So we'll do both those and then we'll call that a wrap right there. Ooh. All right. So I'm not keeping track of time, but okay. Um, Try to make this last close to class period. We'll see. Okay. Number 12, sales. Last month, the retailer sold 120 jar candles at $30 per candle. Hmm. Okay, so just out of curiosity, what revenue is that? 120 candles, $30 per candle. So it's at $3,600 they're making. Revenue. This month, the retailer is considering putting the candles on sale. They estimate that for each $2 decrease in price, they will sell 10 additional candles. Right. So this is really the same scenario as before, except exactly backwards. And since remember before we were selling ski tickets, we're saying, well, if we increase the price, we'll sell fewer, and there's a trade-off there. Here, we're saying if we decrease the price, and right away you say, wait a minute, we'd be losing money because we're getting less money per candle, but we're selling more candles. So we're off to a similar trade-off, right? There's a similar trade-off. Right? So how much should the retailer charge for each candle to maximize, well, again, they say profit, I'll just call it revenue. Okay. Now, if we go back to this example, okay, this one is like revenue equals price times quantity. This is really the starting point. Okay, so everything branches from there. Okay? If you take in you kind of economics class, that should look really familiar. Okay? And we're going to make our own revenue expression. Okay? So the price, remember, starts off at $30 per candle. So it's like $30, right? But then we're going to subtract off $2 price increments. And so $2 price increments times the number of increments. See, it's going to model exactly what we did over here, except over here there was plus because we were increasing the price by $5 increments. So just to really point this out, okay, X, remember, represents the number of $2 price decreases. Okay, so we're going to use that. All right. And then multiply by the quantity. Okay. Now, every time we reduce the price by $2, we'll sell 10 additional candles. Ooh. Well, how many were we selling at the base price? We were selling 120 candles originally, 120. Right? And then plus, right, 10 additional candles per incremental price decrease, okay, which shows it like that. Okay. So this X also refers to that X right there. Okay. Make sure I modeled this correctly. Is that what we did? Yeah, that is what we did before. The only difference is the plus and the minus are backwards from before, but yeah, okay, because we're decreasing the price. Yeah, that's it. Okay. So let's see a few ways we could handle this. I might like to FOIL this out and put this in standard form, and then we can look at quadratic and figure out where's the vertex from there, right? So revenue equals, yeah, let's FOIL, FOIL. So go FOIL. So 30 times 120. Ooh, what is 30 times 120? That's $3,600. Oh, okay, because that was the baseline price, right? So if there was no change at all, they're gonna make $3,600. Okay. Then outside, so 30 times 10x would be that'd be plus 300x, and then the inside 2 times 120, and it's negative, so minus 240x, and then last negative 2 times 10 is negative 20, and then that's x squared. Okay. Okay, so here, I'm just going to clean this up a bit, combine these terms, put the x squared term in front, shuffle things around. So revenue as a function of x, I put it down before, okay, as a function of the price, the incremental price decreases. Okay, that's what, again, what this x represents. Okay, would be, we got negative 20x squared minus, or no, actually plus, wouldn't it be? This would be, what, 60 x, and then plus 3,600. Okay. So here's their revenue equation as a function of the number of like price decreases, right? For x. That's what the size is. All right. So I know the vertex would be at negative b over 2a. Right. Here's like my b term here. Here's my a term here. Right. So that would be at, right, so I'll say x max because this is clearly an upside down parabola, right? Like if I graph this like x and then revenue, there's some kind of upside down parabola going on, right? If there's no price change at all, we're getting $3,600. Then we start decreasing the price. The total revenue actually goes up because we're selling so many candles, right? Now, after a while, so many price decreases. It's like, well, if you're giving away candles for free, now you're not making anything. That'd be like down here, right? Okay. So we're trying to figure out this vertex right here. Like, what is this vertex? Okay. So it's at negative 60 over, say, 2a, which a is negative 20, right? The negatives cancel. And this, that's, huh, 6 over 4? 6 over 4? That's like 1.5. That's interesting. Okay. I was looking for a whole number, but it didn't have to be a whole number. Right? Okay, so 1.5 of these incremental price decreases, which 1.5 times $2. So 1.5 price decreases times $2 decreases would represent a $3 decrease. Right? Therefore, the optimal price would be, well, the starting price, what was the starting price? Wait, was it 30? Yeah, $30. What's $30? Okay. To maximize the revenue, we need $3 less than that. So it'd be $30 minus $3 equals $27. Right? So I know there are a lot of variables shuffled around here. We got revenue, we got number of price decreases, we got the actual price itself. Okay. Yeah. I just looked over at the teacher's edition. They are saying the best price is $27. So that is the answer. Yeah. So $27. All right. So that worked out. Okay. Again, number 11, number 26 are extremely similar to that ski resort example, which is also very similar to what we just did with these candles. Okay. Let's go over to trajectories. Okay, so at a special ceremonial reenactment, a cannonball is launched from a cannon on a wall in Fort Chambly, Quebec. So how the path of the cannonball is traced on a graph so that the cannon is situated on the y-axis, that's like so far above the ground. The equation that describes its path is y equals, okay, and then, yeah, there's definitely quadratic with a negative x squared type term, right? Where x is the horizontal distance from the cliff and y is the vertical distance in feet. How high above the ground is the cannon? All right. So we're getting y equals negative 1 over 1600 x squared plus 1 half x plus 20. Right, so like that. Right? This is all about interpretation. Right? That's what they want to see. Can you correctly interpret what's going on in this situation? Okay, so just point this out. This is the height. You could do f of x or h of x. Maybe I could even call it h of x, right? H of x. That might actually look better. So height is a function of, and what is this x? They said the horizontal displacement. Wait, is that what they call it? Well, distance. It's like a physics term here, right? Say from the wall, right? So for example, if you plug in 0 for x, guys, if you plug in 0 for x, like the cannonball hasn't been shot out of the cannon yet, so it's like at the wall, which is right where the cannon is, like horizontally speaking, okay? Then you'll get the height of the cannon, which would be 20 feet, wouldn't it? Oh, actually, that was the question. How high is the above the ground is the cannon? This is the answer right here. Okay? Right, so height in feet. Okay, so like h of 0 equals 20 feet. That's the answer. That's the answer. Okay. Okay. Now here, I'll have my own extension question because I might ask something different. I wonder how far can this cannonball be blasted? Like if it's sort of map this out, I bet it's going to look something kind of like this. Okay? So we got 20 feet up. You got this cannon. It's going, it's going to go into this parabola path. Okay? Because you throw something in the air and gravity's pulling down. Yeah, it does make a parabola shape. Okay? So I know that this height, uh, call it initial height, is 20 feet. Right? What I might be curious to know is, well, how far downrange is this cannonball going to land? Maybe I'll call it X max. or something like that. Okay. And I see mathematically that's where the height is equal to 0, isn't it? Okay. So I could do this. I could set this whole thing equal to 0 and then solve for x, and that would be the answer. Okay. So I can go -1 over 1600 x squared plus 1/2 x plus 20 equals 0, right? And that would tell me x that would represent this x max. Okay. Oh, and look at that. That's a job for a quadratic equation right there. Yeah. Right. Right. So x max would be at -b plus or minus the square root of b squared minus 4ac. Let's make sure this is all okay. All collectively divided by 2a. All right, that's a lot of fun for the calculator. But yeah, let's give it a try here. If I can get all the parentheses in the right place, and all the negatives in the right place, get the square root in the right place, right? So if I can correctly communicate that. You could, if you want to, you could chunk this down to smaller steps. You could solve this and write that down, and then solve this and write that down, and solve this and write that down, and solve the numerator and write that down. So you could go piece by piece by piece. That's okay. Okay. I'll see if I can do this all in one go. -1/2. Now there's a plus or minus. So let me try plus and see what happens. And I'll go back and I'll put in minus afterward. And square root of b squared. Now two negatives right here. I see a negative, negative. I'll just save myself and just call it plus. Right, they cancel. Okay, 4 over 1600 times 20. Okay, now group that together in parentheses. Okay, that's my radical. Okay, I think we're good. All right, so then collectively divided by 2 times -1 over 1600. Okay, double check, make sure I type that in right. Okay, I think we're all right. Okay. So I'm getting -38.2, or here, what if I go back and I change this plus to a minus? Because don't forget quadratic. Get plus and minus there. Yeah, that looks more reasonable. 838. This would be in terms of feet. So this many feet or this many feet. Now, -38 feet refers to like in the past, like if you completed this parabola, I bet it would sort of go backwards like 38 feet this way. But we're not interested in that. That's kind of not physically what's happening. It's actually going forwards 838 feet. Right, so that's where it lands. It's 830 feet, 838 feet downrange. There you go. There is the answer. It's quadratic.